One of the Incredible Spider-Man's most iconic scenes is his first ever swing from a rooftop. Spider-Man has just realized his power, but has not yet harnessed its full capabilities, as he collides into the wall in front of him. In this video, I'll be investigating the physics behind this swing to discover with just how much force Spider-Man collided into that billboard. Would you or I, an average Joe, survive that impact? The physics can get pretty complicated if you take into effect the force of tension on Spider-Man during the swing and the angle at which he first hits the rooftop. I'll be simplifying the calculations by avoiding these two components, but in the end, avoiding them would have a negligible impact on the end result, only a 2 or 3% change. Solving this problem in one breath would be nearly impossible. There are too many moving parts and variables. To solve this problem, we must break it down into 3 steps.
Tally-ho.
The swing, the skid, and the collision.
Why don't you explain this to me like I am an 8-year-old?
First, we need to find out just how fast Spider-Man was moving when his feet landed on the adjacent rooftop. To do so, we will apply the conservation of energy theorem, which states that the energy of a system must be the same before and after, because energy cannot be created nor destroyed. As Spider-Man stands on the ledge, all of his energy is conserved as potential energy. At the point where he reaches the roof, all of the potential energy has been transformed to kinetic energy. From this, we have the equation for potential energy, or mass times gravity times height, and we can set it equal to the equation for kinetic energy, 1/2 mv squared, where again m is mass and v is velocity. The mass on both sides of the equation cancels out, and gravity is a constant 9.8 meters per second squared. From the video, Spider-Man appears to jump from 4 stories up, which can be estimated to be about 15.25 meters, or 50 feet. Solving for his velocity yields 17.289 meters per second, or 38.67 miles per hour. Now that we know how fast Spider-Man was traveling when he reached the rooftop, we must determine how much he slowed down as he skidded across the roof. To do so, we can use the work energy theorem, which states that the initial energy of a system plus the work done on the system is equal to the final energy of the system. To solve for the final energy of Spider-Man, and thus his final velocity, we must first calculate his initial kinetic energy. Kinetic energy is equal to 1/2 the mass times the velocity squared. Plugging in 5'8" Tobey Maguire's weight of 73 kilograms into the equation, along with the velocity we just calculated, we know Spider-Man's initial kinetic energy was 10,910 joules. Now we must calculate the work done on Spider-Man by the force of friction between the roof and his shoes. The force of friction is equal to the normal force times the coefficient of friction, which is just a constant. In this case, the normal force is simply Spider-Man's weight times gravity, ignoring the tension of the rope. A typical coefficient of friction for sneakers on concrete is 0.5. Plugging in his mass, gravity, and the coefficient of friction, we can calculate the force of friction to be 358 newtons. The final energy is equal to the initial minus the work done by the friction. To calculate the work done by that force, we must know what distance that force was being enacted. From the film, we can estimate the distance to be about 20 meters. Work is equal to force times distance, so in this case equals 7,154 joules. Now, subtracting the work from our initial energy yields our final energy. 10,910 joules minus 7,154 joules is equal to 3,756 joules. Working the final kinetic energy backwards, we can find Spider-Man's final velocity as he approaches his unavoidable collision. The kinetic energy was equal to 1/2 the mass times the velocity squared. Rearranged to solve for the velocity gives the square root of 2 times the kinetic energy over the mass, which equals 10.14 meters per second, or approximately 23 miles per hour. Now that we know how fast Spider-Man is traveling as he approaches the wall, there is only one thing left to calculate: with how much force he is impacted. Applying the impulse momentum theorem, which states that the impulse, which is equal to the force applied over time, is equal to the change in momentum. This theorem can be easier understood through viewing the equation. J, the impulse, is equal to the force the wall applies to Spider-Man multiplied by the time the force is acting on Spider-Man, which is also equal to the change in momentum, delta P, which equals mass multiplied by the change in velocity. Through some rearrangement, we can see that the force is equal to the mass times the change in velocity over the time of impact. We can reasonably assume Spider-Man was in contact with the wall for about 0.2 of a second, and that since he fell to the ground afterwards, his final velocity was 0. Plugging in Spider-Man's weight and speed, The force applied to Spider-Man over those 0.2 of a second is equal to 3,703 newtons. According to Dr. Sidney Burr of the University of Southern California, a force of about 3,300 newtons has a 1 in 4 chance of breaking an average human's ribs, meaning 3,700 newtons surely would have dealt even a superhero some adequate pain. Hitting the billboard with that much velocity would be the equivalent of nosediving off a 17-foot building onto the concrete below.
You thinking what I'm thinking, partner? Aim for the bushes.
In conclusion, unless you two have spidey senses and can climb walls, I leave this stunt to the movies. Although you'd likely survive, a swing from that high up for you or I would likely land us with several broken ribs in the hospital. Not to mention the potential for a broken nose or shattered kneecap depending on how you hit the wall.